information available. You can harass him with a lot of questions. He won't be tired.
I'd be glad to answer it. So thank you, Hugo, for the introduction. So I'll present my work. It is a research paper which is called an objective physically based model for active section phenomenon simulations in collaboration with Christian Dury and Maud Marshall. So the main motivation of this work is that suction cups are widely used in the context of robotics, especially for vacuum grippers, wall climbing robots, and also the soft automatic actuators. So in order to improve the design of this robot, this is necessary to do modeling and simulation of the suction phenomenon. Well, there are quite a few works about suction cups, like the early work from Barr, which designed wall climbing robots. Liu, who does a simple simulation model, simple modeling of a suction cup. And more recently, there is a girl who does a quantitative study about the attachment and detachment of a suction cup, and Miller, who does the suction contact model to evaluate the quality of the seal. But, however, there is no simulation provided in these works, because simulation implies different models. A lot of contact points could lead to high computation costs, and the aerodynamics, in case of suction cups, aerodynamics may have to be considered, right? So we propose an interactive physics simulation of the suction phenomenon. Our contribution are classification algorithm, which is able to detect if the cavity of the suction cup is airtight or not. And we formulate the active pressure of the suction cup as a constraint while considering the classical contact constraints. So there is coupling between contact constraints and pressure constraints. In addition, we have the second part of the work is the evaluation of the model through a comparison with of simulated data with raw data. So in the next slide, I will talk about these two parts of the work. So let's begin with the physics simulation part. So, as you may know, the deformation suction cup is performed using the co-rotational finite element method. It means that from a topological point of view, we have an efficient mesh composed of tetrahedra. And in addition, we have a collision mesh, a surfacic collision mesh composed of triangles for collision detection purpose. So now I will detail the different stage of what happened during one time step. So at the beginning of the time step, the material configuration is computed. We have so it leads to the free configuration of the suction cup. As you can see on this image, it means the constraints are ignored in the first time. Then the collision detection stage occurs, and the narrow phase of the collision detection gives us the localization of the contact points plus their violations. So in case there is no contact, we simply move to the next time step. Otherwise, we run our classification algorithm, a vertex classification algorithm more precisely, and in this way we detect if the cavity is airtight or not. So if it's airtight, we generate different constraints, so the contact constraints and the air constraints direction. As we can see on this image, the red ones are the pressure constraints. Their directions are actually scaled by the local surface area. And in red, all around the seal, we can see in red the contact constraints, and both are embedded into a constraint matrix H transpose. Once we have these directions, the objective is to solve these constraints. So solving these constraints means finding the constraint forces as Lagrange multipliers. So we call lambda as a vector R of all these constraint forces. And thanks to a Gauss-Seidel solver, we are about to find them. When we have H transpose and lambda, we have the constraint forces. We have the constraint forces. So we apply them as motion corrections. And we move to the next slide. So now we detail the classification algorithm. So as I just said earlier, its purpose is to detect the two different states of the cavity. So here is an animation of its progression. So on the right image, is represented the inner surface of the cavity. So first, we classify the contact points thanks to the narrow phase cohesion detection. We have a guess of the inner border. We move this outer border from the inside. So it's a bit similar than the seed field algorithm. And then by detection, we can find the cavities, so the airtight cavities of the suction cups. So it's very similar to the seed field algorithm. And for better understanding, here is a representation of the constraint matrix, H transpose. So here in red, we still have the contact constraints, and in green, the pressure constraints. So we can see that the constraint matrix is a sparse matrix, actually, and we have one Lagrange multiplier per contact points, but only one Lagrange multiplier for all the pressure constraints. So lambda p here represents the scalar pressure. So here is a demonstration of our suction contact model. So we're going down. Then we set the pressure to a negative pressure. It's a bit laggy, I don't know why. Do it again. Yeah, it's a bit better. It's a bit laggy, but we can notice small oscillations. It is due to it's a small due to the discretization of the mesh, actually. So now let's talk about the model validation. So we performed two experiments to compare. So we compared simulation data with real data through two experiments. The first one was to compare the geometry, to validate the geometry, and the second one was to compare the necessary pull force to detect when the suction cup detached. So for these two experiments, we cast two suction cups. So first we mold, we 3D print a mold, and then we cast in silicone these two suction cups in two different industrial materials, knowing their properties, their mechanical properties, so actually the Young modulus. So for the geometry comparison setup, we have the suction cup, which is linked to a vacuum pump. And in between, we have a pressure regulator in order to be able to manually set the pressure and reach the desired shape of the suction cup. And thanks to the camera, we combine photogrammetry techniques. We use photogrammetry techniques to reconstruct the real suction cup as a mesh. And we were able to compare the real suction cup, so the reconstructed real suction cup, with the virtual suction cup, so the simulated suction cup. We compared using a matrix which is called the Hausdorff distance, and as we can see on these under these two images, we reach an average of let's say 2.5 millimeters, which is quite okay, when the pressure is equals to -11 kilopascal. So that's it for the geometry comparison. And for the force measurement experiments, we have this setup. We have the suction cup, which is hooked to a force sensor, and it is fixed to an actuator. So, as the first experiment, we still have the connection between the vacuum pump and the cavity. So for each one of these experiments, the process is split in 3 steps. So we have the actuator which go down. Then we set that once the suction cup touch the plate surface, we simply manually set the desired pressure, and then we move up the actuator until the suction cup detached. So we do this for 4 different pressure values, and here is a video to illustrate that. Let's do it again. I don't know why it's a bit laggy, but we can see it. And here is the result. So the continuous line here represents the real data, whereas the dashed line represents the simulated the data extract from the simulations. We have a time offset of 200 milliseconds for better readability. What is important on this graph is the moment when the suction cup is detached, and here we can see the results are pretty close. So in conclusion, we achieved physics simulation of the suction phenomenon using an active pressure constraint. And this slope is a classical contact constraint. Secondly, by comparing simulation data with real data, so for force and geometry, we proved that our model is close from reality. So as perspective, we would like to do further experiments on these model evaluations, and we would like to apply our suction contact model in robotics for robotic purpose. So thank you for your attention, and I'll be glad to answer your questions.
Thank you, Atona. Is there any question?
Congratulations. Could you use your simulator to design suction objects with different shapes, such as, I don't know, square, banana shaped, or any other? I don't know why, but why not?
Actually, it is possible. However, in our model, as we can see on these images, we simplify the aerodynamics. So in case of real weird shapes, we can't prove that the behavior will be the same as in reality. So it is possible for, let's say, when the shape is still well standard or symmetrics, I think it will be okay. But for more difficult shapes, I think it will be necessary to simulate the aerodynamics in another way. Because here the aerodynamics is not really simulated. It's just we have constraint directions, so we assume the pressure of the air is still in the same directions. Let's say. So in case of very weird shapes, I think the aerodynamics will the behavior of the aerodynamic will be more complex.
Hello. Thank you for your presentation. I have a question about this, the interaction between the cup and the surface where you
Sorry,
are.
the what?
The interaction between your cup,
the cup.
and the surface that
Yeah.
is attaching, because what is the hypothesis that you take here in your model? Because I think that if you are going to in the detail of rugosity of the surface, is gonna change the I don't know how to say that, but the other is
Exactly. Actually, there is an influence of the frictions. So when the surface is more, let's say, bumpy, the friction will be not the same as a very flat surface. In our model, actually, it's not presented in this work, but now in our model, we are able to have additional constraints. We call it friction constraints. We can have a preview here on this image in blue. We have directions. We are parallel to the surface, and actually, it simulates the friction. So in a way, we simulate, we can handle different regularity for flat surface, for different surfaces.
Okay, I had also a question about the influence on the resolution of the mesh. Did you study that a bit? To refine a lot because you said it's actually vibrating due to the mesh refinement.
Actually, I can quickly explain the oscillations we saw in the video. So the points which are on the collision mesh and which are close to the seal oscillate between two steps. For one time step, it is a contact point, and for the second, the next time step, it will maybe become a pressure constraint. So we have a pressure constraint force which acts frequently, creating the oscillations. So to remediate this problem, the very hard solution will simply to have very refined mesh, especially for the points which are next to the section seal. Another solution will be to have a slight transitions of the states. So it will be progressively become a contact point or a pressure constraint with an interpolation, for example, like linear interpolations.
So last question.
Hello. Just a question regarding what is the thickness of the membrane of the cup?
I don't have the.
I mean, is it problematic to mesh with a tetrahedron? Is it quite thin? Could you, for example, use like a shell model to represent the
What?
like
Shell model?
Shell model. I'm asking if it's very thin, the cup. Maybe it's quite challenging to mesh it with a tetrahedron.
You mean
or you don't actually have problems with that?
I don't investigate that. However, of course, we could we could generate the tetrahedron mesh using a smart approach.
I mean, in your case, so it's not a big deal actually. Okay.
So you mean when the
I mean, it's quite challenging sometimes to mesh a thin surface using volumetric elements like tetrahedron, but apparently it's not so problematic in your case.
Yeah, but of course we could improve it.
No, if it would be enough for you.
And I think the question behind is also the stability, which when you've got and the accuracy, when you've got only one tetra in the depth of your membrane, here you might have basically an accuracy of the FEM model. But
yeah, sometimes I understand the question. So, of course, we could have a complete tetrahedron between the two. That's what you want.
Yes, what I mean.
Yeah, only one tetrahedron for which goes from the one side of the surface to the other side of the surface. Actually, I think it's the case. So we could like to improve that and see if there is a different behavior of the solutions. Would be very interesting. I didn't notice that. So thank you.
Thank you. Thank you again.